Our journey to understand the cosmos is also a journey to understand time itself. Around 1500 BCE, ancient civilizations created sundials, nature's first clocks, using the sun's shadow to mark the hours. Soon after, by 1400 BCE, water clocks, clepsydras, measured time with the gentle flow of water, inspiring awe with their ingenuity. These early clocks brought order to the seasons, to life, and to the rhythms of ancient societies. But sundials and water clocks depended on weather and environment, and their accuracy was limited. In the 1300s CE, mechanical clocks appeared, powered by gears and weights, revolutionizing timekeeping in medieval Europe. Then, in 1656, the pendulum clock brought breathtaking new precision, dividing days into hours, minutes, and seconds. Clock towers became the heartbeat of cities, synchronizing communities and inspiring progress. Each advance was a triumph of creativity, yet even the finest clocks faced challenges: friction, temperature, and wear. For science and navigation, even the smallest error mattered. So the quest for perfect timekeeping pressed on. The next leap came from quartz, a crystal that vibrates at a precise frequency when electrified. This piezoelectric effect made quartz clocks far more accurate than any mechanical device. Suddenly, reliable timekeeping was everywhere on wrists in cars and homes. Quartz clocks powered the 20th century timing broadcasts, phone calls, and computers. Their accuracy, losing just a second a year, seemed magical. But even quartz has limits it ages, and its frequency can drift. For most, this was good enough, but for science and technology, it wasn't perfect. To explore the universe and build global systems, we needed even greater precision. The search for the ultimate clock continued. We needed a timekeeper that ticked to the rhythm of the universe itself. The answer lay within the atom. Atoms, like cesium, have electrons that jump between energy levels, emitting microwaves at a constant frequency. Atomic clocks use this property, tuning microwaves to match the atom's natural rhythm. When the frequency is perfect, the atoms respond, and the clock locks onto this unchanging beat. The result? Unmatched precision. A cesium clock might lose a second in 300,000 years. The latest atomic clocks are so accurate, they wouldn't lose a second in the age of the universe. This precision underpins our modern world. Science, navigation, and communication all rely on it. Building these clocks requires pure materials, perfect vacuums, and flawless engineering. Atomic clocks are a triumph of human ingenuity, where quantum physics meets masterful craftsmanship. They let us listen to the fundamental ticking of the cosmos. Our understanding of time had reached a new frontier, but the story didn't end there. Atomic clocks now weave the fabric of our civilization. GPS satellites use them to pinpoint your location. An error of a microsecond means hundreds of meters off. Banking, the internet, and power grids all depend on this invisible network of perfect time. Even Einstein's relativity is confirmed. Atomic clocks tick slower at sea level than on a mountaintop. These clocks let us measure the warping of space-time itself. Now, scientists are building quantum clocks with atoms like strontium, even more precise than cesium. They can detect changes in gravity by moving just a few centimeters. Soon, we'll map Earth's gravitational field in exquisite detail, predicting eruptions, finding water, and more. The story of timekeeping is humanity's quest for the absolute. From shifting shadows to unwavering atoms, we organize our lives and unlock the universe's secrets. Our journey through time continues, ever more precise. The cosmos still has mysteries to reveal.